You want to okay, perfect. So welcome everyone. Um Today we have with us Dimitioskosmopoulos with us. He is a theoretical physicist specializing in high energy physics and gravitational theory. He completed his PhD at the um, California University and under the supervision of Sevi Byrne, following a postdoc at the University of Geneva. Uh, he is currently a postdoctoral researcher in the Department of Theoretical Physics at CERN. And thank you for to stay with us and present your work. We are very happy to have you. So you can start at any moment. Thanks.
Yeah. Okay. Thank you. Thank you for the introduction, and thank you for the invitation and accommodating this earlier time slot. So today I'll be telling you about love numbers. This is based on a paper that we put out in December with the same title, together with David Perrone, who's finishing his PhD at the University of Geneva, and Michael Solon at UCLA. Okay, so before I start, I want to give you maybe a little bit on the background, how I came to be thinking about this problem. So I am part of a community who has been over the past few years trying to use particle physics tools that have been developed over, say, the past 50 years or so for collider physics, use these tools for the modern experimental frontier of gravitational wave science. So for me and for many of us, this pipeline looks a little bit like this. So we start with these tools, say effective field theory, Feynman integration, and compute a 2-to-2 scattering amplitude. Now this amplitude looks very much like it would in, say, QFT class, but instead of imagining scattering elementary particles, we imagine scattering astrophysical objects. In particular here, at the end, I want to study a binary system that emits gravitational waves, and I imagine instead of the two members of the binary being in a bound orbit, I imagine them being in a scattering orbit and computing the scattering amplitude for that process. Okay, once I have computed this amplitude, I can quote unquote Fourier transform to get a two-body potential. Now, maybe this you've also seen in QFT class. Maybe you computed 2-to-2 scattering for, say, electrons in QED, took the non-relativistic limit and Fourier transformed to get the Coulomb potential. So in a process very similar to that, we can get the Newtonian potential, but then also an infinite tower of corrections. And these corrections can come from higher order in the coupling or from finite size effects like the spin or tidal deformability, etc. Now, importantly, even though we obtain this potential from scattering, we can then use it for the bound orbits that are phenomenologically relevant. So this is why it doesn't matter that we start from this different regime. Okay, so once we have this potential, then our job is done. We hand over this potential to our friends over at LIGO Virgo Kagra, and then it fits into their pipeline, which eventually produces waveforms, which are used in the experiment for detection. Okay, so today I'll tell you about tidal deformability. And when we talk about tidal deformability, we take a small detour. We don't compute directly due to two amplitudes. We instead consider first wave scattering of one of these objects. And when we describe this process in this effective field theory description, there is a lot of Wilson coefficients that enter our description. And some of these Wilson coefficients are what in the GR literature we refer to as log numbers. So in particular, if you are used to be thinking from a QFT perspective, log numbers are just some special Wilson coefficients that I'll be interested in. And if you're more used to thinking from the GR perspective, log numbers are what capture how much can a body be tidally deformed. Okay, so this is the object that we'll be computing today. And once we have it in our effective description, which can describe all compact bodies at once, if we want to describe a particular object, let's say a black hole, then we have to match to some full theory. And then we'll see how we match today to black hole perturbation theory to extract log numbers for black holes. Okay, so now once we have our description like this and our wave scattering under control, then this feeds back into the 2 to 2 amplitude and we continue with our pipeline. And perhaps it's not obvious from the leading order, but once you look at the next leading order, you see exactly how the Compton amplitude fits into the pipeline. Okay, so today we will do this first steps. We will write a new effective theory, cell effective field theory, which is tailor-made for this computation, and we will use it to compute new love numbers. And our approach to this problem has very much the amplitudes flavor. In amplitudes, we often try to come up with a new method of computation that will allow us to obtain new results that were impossible or really hard to obtain in the past. And by analyzing these results, we hope to find some new structure which will then allow us to sharpen our tools, get more results, and so on and so forth. So with this work, I'm happy to report that we managed to do one loop around this virtuous cycle. So I will tell you about a new method called shell effective field theory, which is a four-dimensional EFT that incorporates solutions to black hole perturbation theory. These are solutions that are in principle known to all orders in the coupling G Newton. Using this setup, we were able to compute for the first time scalar log numbers through g to the 9. This, to give you a sense of the calculation, this would require an 8-loop calculation in field theory, but we were able to do it without performing any integrals. This is for generic objects, any object you want. Specializing to black holes, we were able to conjecture from this high order data an all orders formula for the structure of the black hole love numbers. Okay, so this is the plan for today. Okay, so after a brief introduction, I will tell you about what cell effective field theory, and then I will tell you how we used it to obtain some new results, and then I will close. All right. Okay, so what are love numbers? The physical picture that we have in mind here is the Earth-Moon system. So we imagine the moon orbiting the Earth, and as it's orbiting the Earth, it's pulling on, let's say, the oceans of the Earth through a small gravitational perturbation, which I depict here with these 3 lines. And as the oceans are pulled and move, they themselves generate a response, a secondary wave coming out of Earth. And this is this response that I'm plotting here. And this now can tell us about the structure of the system, so the structure of the object. So in particular, if you have a planet that has a lot of water, then it will respond more than a planet who doesn't. Now, why are these numbers particularly interesting? Well, first off, they have a very special property that the static limit of love numbers is 0 for black holes in general relativity in 4 dimensions in asymptotically flat spacetime. So this is a very specific and very phenomenologically relevant case, and that's why it has brought a lot of theoretical study on it, because this vanishing of the static love numbers is unnatural from our general EFT principles, and then people are trying to understand in terms of some symmetry that prohibits their appearance, etc. But beyond the theoretical intrigue, it's also of practical importance because if you are studying a system, a binary system, where from your astrophysics you believe that you're talking about black holes, and you're measuring these numbers to be non-zero, then perhaps you're measuring beyond GR effects. Okay, so now the vanishing of the static love numbers is a somewhat known fact. Even if you're not working in this field, perhaps you've heard of it. Today, I want to tell you that we found that the dynamical love numbers as well are also very special. So this simplicity that we see in the static sector seems to extend to the dynamical sector as well. These numbers are not zero, but as I will show you, we discovered that they follow a very particular pattern. But more on that later, just to keep you engaged. Okay, so even if you're not talking about black holes and you're talking about, say, neutron stars, log numbers are particularly interesting because they teach you about the equation of state of the body. Think again here about the ocean example that I mentioned above. Okay, so these are the reasons why log numbers are a principal goal of the gravitational wave program. All right, so what I want to do next is I want to demonstrate to you this fact that the static log numbers are zero. So it definitely sounded magical to me before I entered this field, but it's actually something that we can see very, very simply. Okay. Now, disclaimer, before I continue, eventually I want to be talking about gravitational perturbations, gravitational waves. So this would be the graviton propagating on top of a black hole. For simplicity, we started instead with scalar waves. I will be referring to these waves as the toy graviton. This is just a simpler case because there's fewer indices. It's a standard toy model for people to start, and there were results in the literature to compare against. The graviton case, the true graviton case we are working on right now. Okay, so let's consider the scalar. And now what we're trying to do is we're trying to solve the wave equation for the scalar outside of a non-spinning compact object where the scalar sees a short-tailed background. And we're taking the static limit, so time derivatives are zero. We have to solve this Laplacian equation. And the very nice thing is that this Laplacian equation, after parse wave decomposing, maps to the Legendre equation. So you can solve it immediately in terms of the Legendre polynomial and the Legendre function. And just like any second order differential equation, you have two free coefficients, which I call here A and B. Okay, so let's gain some intuition about this. So what I'll do is I will expand around infinity. And what we find around infinity is that the Legendre polynomial grows. It is a polynomial after all. And then the Legendre function decays with distance. This allows me to put some labels on these two pieces. In particular, we can think of the Legendre polynomial as the perturbation that we turn on and the Legendre function as the response. Why? Let's think of a simpler case back in electrodynamics. Imagine taking a conductor and placing it in a static external electric field. Let's say that the electric field is constant along the z-axis. The corresponding potential is increasing along the z-axis. So at infinite distance, it increases. Now the conductor will have a dipolar response to this electric field. And that field, the dipole field of the conductor, will decrease with distance. So with this intuition, I can assign these labels also here in the gravitational case. Okay, now we define the love number, the static love number, in the following way. We take our solution, we expand around infinity, and we pick up the coefficient of the leading increasing term and the coefficient of the leading decreasing term. We form this ratio, and by definition, that is the love number. Okay, so let me do this for this particular solution that I'm writing here. If I do this, I can find immediately that the log number is some coefficient and then b over a. Okay, so now if you're thinking, well, is this definition Gates invariant? You used here some particular coordinate system. What happens if you change coordinates? Well, this definition is perfectly fine, but let's keep this concern and we'll come back to perhaps more nicer definition in a couple of slides. Okay, so this now is for any object. Let's focus to black holes and see what happens. So for black holes, we have again the same equation, the same solution. What tells a black hole apart from a different object is what happens at the horizon. So we will take the solution and we'll take the opposite limit and go and sit on top of the horizon. So in that limit, what happens is that the polynomial goes to a constant and the Legendre function blows up logarithmically. However, we don't expect anything weird to be happening at the horizon, so by demanding regularity, we find that this second coefficient, the b, must be 0. And I told you that the love number is basically b over a, and therefore the love number, the static love number for black holes vanishes. So as simple as that, we demonstrate the vanishing of the static love numbers. Okay, so this is the definition of love numbers in general relativity. Now I want to have a different definition. And I want to use the language of quantum field theory, the language of Wilson coefficients, renormalization group, etc. Okay, so how do I do that? Well, what I'll do is I will match the full theory description, let's say a black hole or the Earth or a neutron star in general relativity, to an effective description where I will describe these compact objects by a point particle, non-minimally interacting with this wave. Okay. So what does this effective description look like? Well, it's given in terms of two pieces. First, we have the bulk, so the free propagation, quote unquote freeze in curved space, the free propagation of the wave. So here we have Klein-Gordon for our toy graviton. For the true graviton, we would of course have Einstein-Hilbert. And there's a second piece that captures the interactions of the compact object with the wave. Now there's many different ways to write this second piece. Here I'm using a word line. You could have used the quantum field theory, or as we'll see later, you could have used the shell. But here for simplicity, I'm just writing a word line. And this word line has the mass term of the word line, and then an infinite tower of operators that captures the interactions between this word line and the field. Now, these are the terms that we want to study, and if it was just for these terms, then the calculation would be very, very easy. The diagram that comes out of this term is very similar to lambda 5 4 theory. Basically, this diagram is up to a number, it's just C naught. The hard part of this calculation comes from the minimal coupling, the minimal coupling between the wave and gravity and between our compact object and gravity. This minimal coupling is mediated through the true graviton. So to consistently compute, you have to include all these, let's say, bulk interactions as well. And then the complication here is that these operators, these counter terms, if you wish, they turn on at some high order in the coupling. And so you have to compute some high loop order minimal coupling diagram to go together with this simple diagram of the counter term. Okay, but let's say you're strong enough, you can do this calculation, you get the Compton amplitude, you match to the full theory description, and in this way you obtain these Wilson coefficients C. The claim that I will come back to later on is that once you have these Wilson coefficients C, then you know the corresponding love numbers as well. But now this definition goes through Wilson coefficients, effective field theory. If you find some scale dependence, you know exactly what it means, etc. Okay, so now here comes a small paradox. I told you that the calculation in the effective theory requires hard loop integrals at high orders. However, in full theory, the problem has been in principle solved to any order in the coupling using black hole perturbation theory. I will review this a little later on. So this is a little bit of a paradox because usually effective theories are easier. You remove some of the physics at small scales, and then your description becomes simpler. So how come the effective theory is harder than the full theory? So that was our motivation and our idea. Can we take these techniques that people have developed for black hole perturbation theory, for the full theory, and apply them in the effective theory calculation that we want to do? Okay. So this is the idea behind our new method. Okay, before telling you about the details, just a few more words on effective field theory. Effective field theory is just a formalization of the simple idea that from far away, any compact object looks like a point particle. Whether the compact object is a black hole, a neutron star, or your favorite pet, we can describe all of these compact objects at once by a point particle, by a point particle together with an infinite tower of operators. Okay, but as we very well know, a point particle description is divergent, and we need to regularize it. And I say here, this is familiar from QFT, but this is familiar already from undergraduate E&M, when we learned that a point charge has a 1 over r potential. So if you ask a question about bringing a second charge on top of the first, then you get a divergence. That's the sort of divergence that I mean here, and we need to regularize it to make sense of it. Okay, can we use the best scheme in the world, dimensional regularization? Well, at face value, at least, we cannot use it because the black hole perturbation theory solutions that I want to use do not exist in 4 minus epsilon dimensions. They exist in 4 and in some integer dimensions, but not 4 minus epsilon. So at least at face value, I cannot use dimensional regularization. So instead, we came up with something else. Well, the simplest thing you can imagine, we stay in 4 dimensions and we use a cutoff. Now our cutoff is in position space, and that's why it takes the form of a shell. Okay, before moving on, I just want to mention very recently there was another paper studying the same problem where they did manage to build a hybrid between black hole perturbation theory in 4 dimensions and dimensional regularization. So perhaps there is a path there as well. That's also very exciting. But for us, we're sticking with 4D all the way. Okay, so we came up with a new scheme, but again, the simplest thing you can imagine, you replace the point particle with a shell. And now we'll claim this is a good scheme, and the reason is twofold. First, we didn't affect the long distance physics. So from very far away, you still see black hole geometry. You cannot tell the difference between a point particle and a finite shell. However, if you go to small distances, because inside the cell you have flat space, you can now touch the origin, and there's no divergence at the origin anymore, and all divergences are controlled by the scale that I introduced, just like epsilon in DIMREG or lambda cutoff in cutoff regulator in QFT. Okay, perhaps this is too abstract. Let me give you just a very simple example. Again, this very familiar example from undergraduate E&M. So I told you that the point particle is divergent if I ask a question about bringing a second particle on top of the on top of this one. So what do? Our cell scheme is just replacing this point particle with a conductor. A conductor has the same potential outside the cell of the conductor, but inside the conductor we have a flat potential. And now we can take a second particle and touch the origin with no problem. Some very simple remarks here. The potential outside, there is charge on the surface of the shell, which we can see by the fact that the derivative of the potential is discontinuous. That tells you that this charge is sourcing the potential outside. However, the potential itself is continuous, and that is a requirement such that at the level of Maxwell's equations, you don't get a divergence worse than delta function. And that's what I say finite charge on the cell surface. Okay. Now, slightly more sophisticated, we can do the same thing in general relativity. We can glue together two spacetimes. So we'll have black hole outside and flat space inside. And same comments here. We see that the derivative of the metric is discontinuous. That tells you that there is mass on the cell's surface, and that mass is sourcing the geometry outside, the black hole geometry outside. However, the metric itself is continuous through the cell, and that tells you that at the level of Einstein's equations, you won't get a divergence worse than delta function. These two properties here, which are very similar to the Gauss law that I described in ENM, go by the name of junction conditions in the GR literature. Okay. Okay, so that's the background, and now we're ready to write the effective theory. So I just need one more technical point before I give you the effective theory, and that is the fact that I will need to use the so-called in-in formalism or Swinger-Keldysh. And the Swinger-Keldysh formalism, I use it because we have dissipation, so we have things going down the horizon. And this is when Swinger-Keldysh is useful. And the Swinger-Keldysh formalism, let me explain it first in a simple example. So here we see in the bulk we have Klein-Gordon, the normal Klein-Gordon. This is conservative dynamics, so you don't have dissipation here. And when you have a conservative action, then the Swinger-Keldysh formalism is just an algorithm that tells you start with the field that you had, you double the field, so that's why I'm writing the two fonts. They both correspond to the same field. Double the degrees of freedom in a particular way, algorithmically, and arrive at your in-in version of the action. So this is just normal Klein-Gordon in the in-in formalism. But this doubling of the fields will allow us to write dissipative terms as well. So here is now the interaction of the wave with the cell. So what does this EFT look like? So first, the volume element. So here, to write the action for a cell, first let's think about how do we write our action for a point particle. For a point particle, we write a word line, and then for a string, we would write a word sheet. So now for a cell, we write a word volume. So this is the word volume element of the cell. This is a normalization, convenient normalization that I picked. This is the term that sources the background geometry. It will not be important for me today. And finally, these guys here give the interactions of the cell with the wave, just like for the word line before. So these operators, they just like in any EFT, each operator comes with its own Wilson coefficient, and then they're built out of more and more derivatives. And the sort of derivatives we have here is time derivatives and angular derivatives. This is the two types of derivative that you get on the cells on the word volume. Okay, and now you can see here the dissipative effects. If this n, if the number of time derivatives is odd, then under normal conservative dynamics, this term would be a total time derivative. So it wouldn't contribute. But now that we have doubled our fields, we are able to write these dissipative effects as well, these friction type effects as well. Okay. So now, finally, to reiterate, the goal here is to solve for the dynamics, extract these Wilson coefficients in terms of the dynamics, and then at the end, take the cell radius to 0 and recover the point particle limit. Okay, so now we could go and compute amplitudes, but I told you that this requires hard loops. So instead, let's do what they did for black hole perturbation theory, which is solve the equation of motion. Okay, so now we start with outside of our body. This is the hard part of the equation of motion because there we have the non-trivial geometry, black hole geometry. So what we'll do is we'll parse a wave decompose just like before. And now the magical thing is that the equation for this radial piece has been solved since the 80s and the 90s. This is what I will be referring to as the MST solution. So this solution exists in principle to all orders in the coupling. And it has this following form. The radial dependence is through these Coulomb wave functions, which are known functions in the mathematical literature. And what you need to do is you need to compute order by order this renormalized angular momentum nu and these coefficients b. Now, in these two papers, Lieber and MST, they give you the algorithm to do this order by order without performing integrals. And importantly, if you're interested in truncating to some order in G Newton or equivalently to some order in RS, then these sums truncate and you have the exact answer to that order. Okay, finally, we see that we have two free parameters, just like any second-order differential equation, A and B. These describe the compact object in question. And since we're doing EFT, we're describing all compact objects at once. This A and B we cannot fix within the EFT. We fix them by matching to full theory. And more on that in just a second. Okay, and this is exactly how we overcome this difficulty of having to do loop integrals. By solving this equation of motion order by order in omega rs, we capture the effects of the loops. Okay, so now, how do we find the A and B? We match full theory and effective theory. So now let's imagine we do first the full theory calculation. So imagine we're talking about an object with some radius RB, B for body, let's say the Earth or a black hole. So, and then we want to match the physics of that object to our cell. The physics, importantly, very far away from the object. So what we'll do is we'll solve the wave equation outside the object. It takes this form that I just showed you in the previous slide, simplified the notation a little bit here. So as long as I'm outside, then I have this form. And again, what I mentioned before, this part of the solution is universal. It doesn't depend on the body, it just depends on the fact that outside non-spinning compact object I have Schwarzschild geometry. What depends on the body is these coefficients. So here I gave them the F and T superscript, that's for full theory. And this I find by going and touching the radius of the object, the surface of the object, and demanding some boundary condition, just like we did at the beginning. Okay. Now for the effective theory, we have a very similar solution. Here I'm not giving superscripts to these A's and B's. And these A's and B's I will not find by the boundary condition. Instead, I will find by matching. And so how do we match? Well, we go really far away from both bodies and we demand that the physics is the same. So the physics is the same means that these A and B of the EFT are the corresponding ones of full theory. So note here, usually what happens is the boundary condition at the surface of the object gives you A and B. For the EFT, you first get A and B from matching, and then A and B will eventually tell you what cell do you need to pick such that your special cell recovers exactly the physics of the body you're talking about. It's the reverse logic. Okay. But now we have the full outside solution. Let's move along. That was the hard part. We're basically done. Now inside we have flat space. So the solution is very simple. Inside a flat space is we just have Bessel. And now we only keep the Bessel function that's regular at the origin because as we said, our regularization procedure, the point is to make sure that there's no divergence at the origin. Okay, by now you know the drill. We have continuity of the solution across the cell. This fixes the two parameters of the inside solution against the outside solution. So we fix the omega tilde and the A tilde. So there's no new freedom on the inside. And we have the discontinuity of the derivative, and that tells us that on the surface of the shell, there is some charges, just like the E&M analog. Okay, and we see here that we first get the A and B, and then from A and B, we get the, if you use the boundary condition, the charges on the shell. Okay. Okay, so that was the bulk. Now, finally, we have the contribution from the cell action. And here, this is a reminder of the action. And then by some simple steps, partial way of decomposing this, very easy, you get this expression at the level of the equation of motion. Now you put it together with the bulk contribution that we just computed, and you arrive at one of the main results of our paper, which is non-perturbatively an equation for the Wilson coefficients that appear on the shell in terms of the discontinuity of the wave solution. Okay. So now let's put this to good use. Let's do first a simple example, the static limit that we discussed at the beginning. So in the static limit, I am taking omega to 0, and my formula simplifies to this form here. And in the static limit, I don't need this MST machinery. I just have, as I told you, the Legendre functions at the beginning. And here, let's think about black holes. So as I told you, for black holes, we have B equals 0, and we just have the A coefficient. Okay, let's plug in and see what happens. So now what's the order of operations? So we plug in our solution, and first we expand in RS, and then we take the cutoff to 0 limit. Why? So this is exactly what we do in quantum field theory. First, we choose at what loop order do we compute. This is the order in RS, or equivalently, the order in G Newton. And then once we have a fixed loop order, let's say 2 loops, then we remove the regulator. So that's why we do the limits in this order. Okay, so let me give you a collection of results. So here are some results. What do we see here? Number one, we recover the vanishing of the log numbers, uh, in these Wilson coefficients. Great. Number two, we see that beyond the zero log numbers, we also get parallel divergences at higher orders in the coupling. Now, this is something that we have to live with when we use a dimensionful scheme, like a cutoff scheme. And okay, it's some feature of our scheme. It wouldn't happen in dimensional regularization, but nevertheless, it's understood why it's there. Okay, great. So we recovered the black hole answer. Now let's do for a second the generic answer. Still static limit, but any object you want. And now the solution has A and B with A and B free. And we do the same steps. And what we find is that up to these parallel divergences, we get basically B over A. And now I remind you from the beginning that the log number also turned out to be B over A. And hence, by plugging in the numbers, we find that the Wilson coefficients are up to a number, the log numbers, and then we have these parallel divergences. Okay, so this is the claim that I made at the beginning. Once you know the Wilson coefficient, you know the log number. Now, this is the logic that I will follow in what is to come. I will basically drop the parallel divergences and analyze mostly the finite part. Okay, let's do the real thing. Let's do the full dynamical case. So here we have the MST solution that I described instead of the simple Legendre functions. And we have A and B coefficients just like before. Here, what I'll show you is the result for black holes. So I have computed A and B for black holes. It's not as simple as B being 0. It's more complicated. But nevertheless, I have computed it and I have plugged in, and what I'll show you is the result for black holes. Okay. So this is a collection of results. So before I was showing you n equals 0 and different l's. Here I'm showing you l equals 0 and different n's. Okay, so now what do I want you to see here? So here I want to compare with results in the literature. So before our calculation, these two groups had computed these log numbers, some of these log numbers, to some lower order in the coupling using the standard dimensional regularization. Okay, and we want to see how do we compare with our different scheme. Okay, number one, whatever is scheme independent agrees between our calculation and these earlier calculations. Number two, what is scheme dependent need not agree between the calculations and indeed does not agree. Now, how can I tell apart what scheme dependent and what scheme independent? Now, if something is finite at some particular order in the coupling, then that is a scheme independent piece. So this 0, this 1, that's finite, the coefficient of the log. If something is not finite, so for example, this number here at this order, so r is cubed, is coming together with a log. So formally, this is not finite. And a different thing we could say is if I change my scheme a little bit, if I shift the size of the shell, then this log will give a number, and that number will change this number here. So in this way, I can see that some of these pieces are scheme dependent. These guys do not agree between the different schemes. And the same logic here. The coefficient of log square is scheme independent, but the coefficient of the log, because it's sitting underneath the log square, this coefficient is scheme dependent. Okay. Finally, we get these parallel divergences which do not exist in dimensional regularization, and hence they are also scheme dependent. And yeah, there's nothing to compare against with dimensional regularization for these, but okay. All right, so basically whatever needed to agree does agree, and the rest it was expected that they wouldn't agree, and indeed they don't agree. Okay. So now I want to show you the full result for L equals 0 dynamical love number through g to the 9, where I have removed the parallel divergences. Okay, so this is the full answer. And why I'm showing this to you is because number one, I'm really happy about this result. So this would honestly require an 8-loop calculation in field theory, and we got it here without doing any integration. This is one of the highest results in perturbation theory, and without supersymmetry or any simplification like this. So I'm really happy about this result. But I'm also showing this to you because at the beginning, I promised you simplicity in the dynamical love numbers. So I want to pose a small challenge. Can you see the structure that defines this love number? Okay, I'm not giving you enough time to figure it out, so I will spoil the answer. So what I was showing you is this F bar, which is written like this, just like we were writing before. Basically, the Wilson coefficient minus any power law divergence. Okay, so this lambda now is written in terms of n pieces. N, again, is the power of omega. These n pieces, furthermore, are ordered in terms of their transcendental weight. So now, a quick reminder on transcendental weight. This weight basically counts the power of pi. So the weight of pi is just 1. The weight of the log, because logs and pi's always come together, is also 1. The weight of the Riemann zeta, now the Riemann zeta for even ends is basically pi to that even power. So we assign the Riemann zeta weight n. And then for odd ends, the zeta of the odd ends, they're not related to pi's, but nevertheless we extend the weight to those as well. Finally, rational numbers, they do not carry any weight because there's no pi's in rational numbers. And for this construction to make sense, the weight of a product must be the sum of the weights. So the weight of pi squared must be twice the weight of pi. Okay, so that's transcendental weight. So this expression is organized in terms of transcendental weight. So we see here, this is the leading transcendental weight number, and it has weight n minus 1. The next term with 2 zetas has weight n minus 2. Then the term with 3 zetas has weight n minus 3, and so on and so forth. We go from weight n minus 1 to weight 0, and hence n terms. Okay, now you can ask, where did the logs go? We were seeing a lot of logs in the expression before. Now the log has transcendental weight 1, and so does zeta 1. Now zeta 1, the Riemann zeta 1 is infinity, so it's ill-defined. But formally, so the log is also infinity. Remember, we're trying to take the radius of the cell to 0. So this is what we came up with, is we define a regularized version of zeta 1 to be this particular log here. So now you might be thinking I'm cheating, but I only get one definition to make this work, so this is quite non-trivial. And finally, the only thing that's left is this matrices L here, and these are just rational numbers, so no more transcendental weight. Okay, furthermore, these rational numbers are universal for the scheme-independent coefficients. Scheme again means cell versus dim-reg. They're universal in the sense that they do not depend on n, and they do not depend on these indices a. And this is huge because n is the power of omega, but also if you fix the angular momentum, n is the power in the coupling. So you read these numbers off at some low order in the perturbation theory, and then you can predict them at higher orders. Okay, so now this maybe doesn't sound so simple, but with this structure, this whole page that I showed you before for the scheme independent pieces reduces to just 4 numbers. Okay, let's see how it works. So let's put back the answer that we had and our conjecture for the all-order structure of the black hole love numbers and see how it works. First, let's hunt for the leading transcendental weight term. Okay, so I told you the power of omega minus 1. So we go omega to the 8 and we see a zeta 7. Omega to the 7, we see a zeta 6. Remember, zeta of an even integer is just pi to that integer. Omega 6, zeta 5, and so on and so forth. If you plug in minus 2 in this formula, then you can predict all of these numbers that I've circled here in green. Okay, let's go next to leading transcendental weight. We go down by 2, omega to the 8, we find zeta 6, pi to the 6. We find zeta 3 squared and zeta 5, zeta 1. Remember the log is zeta 1. And so on and so forth. If you plug in 22 over 3 in this formula, you get all these numbers. And we continue like this for higher transcendental weights. And it works like these colors here. So now some comments. You see that after the leading one is just 1 per order. The next leading one, you measure 1, and then you predict 2, 2, eventually 3, and more. So you read off a few, and then you predict infinite towers. And then finally, there's some numbers here that I didn't circle. These are scheme dependent. So for those, we didn't find some nice structure. And perhaps those are the less important ones because these would be different in dim-reg, say. But how the structure that I'm showing you here, the ones that I have circled, these would be the same in dim-reg as they are in our scheme here. Okay, so I'm really happy about this, but love numbers are a gift that keeps on giving. So it turns out that you can do more with this structure. So if you assume that our conjecture holds to all orders, then what you can do is you can resum it. And you can resum it one by one. So you resum first this one, then this one, and so on and so forth. You can do them all because of this universality. It basically just boils down to the same sum squared or cubed or so on and so forth. Okay, so after your sum, you get such an expression. And this expression is written in terms of one special function, the harmonic number, which has now been analytically continued to the complex numbers. Okay, and it's written in terms of this parameter eta, which is just I omega rs. So now we started from, even though we started from perturbations in omega rs, we were able to resum, and now we can ask questions about when omega rs is even order 1. So make contact with the non-perturbative physics. And we can ask what is the structure of this function in this complex plane. And what we find is that it has poles at integer spacings of these imaginary units I over rs. Okay, so now you can ask, where do you expect this function to have poles. And then the love numbers are expected to have poles at the locations of the quasi-normal modes. And the quasi-normal modes in a specific limit, which is called the large overtone limit, so you basically take this integer n and you expand around a very large n, they look very, very similar. They have integer and half integer spacings in these units. Okay, so it looks like we're almost getting there. It looks like we right in some sense, but we need to do better to understand this, and hopefully we can get it by some extension. Okay. Okay, so now I'll close. First, I'll tell you what I'm thinking about for the future. So now I believe there's things to do when it comes to effective field theories, matching, and renormalization in classical theories. This is not the first paper to touch on this subject. There's been many works in the past, but I believe there's still a lot to do. And in particular, something that I'm excited about is, could we combine the resummation from the normalization group, which basically resums the logs, together with our conjecture and the resummation that our conjecture allowed? Could we put these two together and predict the quasi-normal mode spectrum? This is something that I'm excited to look at. But then there's natural extensions of this to other cases, in particular to the really interesting case of the graviton. So we're working on the graviton right now, and eventually we want to promote this setup to the Kerr black hole as well. Okay, so now I want to just mention that this is not just a method to tackle love numbers. This is a method to go all the way to the potential, as I described at the beginning, through the pipeline, all the way to two-body observables. And how am I envisioning this program? So what we constructed today, this regularized solution, can give you the propagator of this toy graviton in the Schwarzschild background. And eventually, by doing the full graviton, we'll have the graviton propagator in this Schwarzschild background. This is the key ingredient for a full curved space QFT framework for two-body observables, where heuristically how this looks like is as follows. We imagine adding a secondary, a companion in this black hole geometry. To leading order, this companion will move on a geodesic, and then this geodesic will source these perturbations. These perturbations will propagate on this black hole background. This is the problem that we solved today. And then eventually these perturbations will hit back the secondary, and this will give you the deviation to geodesic motion. Okay, so in this way, one can study the full two-body problem, and a first preliminary analysis of this should appear soon. Okay, now to summarize, I told you how we developed a new method, cell effective field theory, which combines knowledge from quantum field theory and solutions to all orders from black hole perturbation theory into a unified framework. In using this new method, how we computed new results for dynamical love numbers through g to the 9, which corresponds to an 8-loop calculation in field theory without doing any integrals. And finally, I told you how by specifying to the case of black holes and analyzing the results, we were able to identify a new structure for the dynamical love numbers for black holes. We conjecture that this structure holds to all orders in G, and if it does, we show that one can resum it and make contact with non-perturbative physics. Finally, I argued that this is a path for the full analysis of the two-body problem in general relativity. And just to show you a picture of where we are and where we're going with this program, after heroic calculations of different groups, we are able to have potentials or equivalent observables at order g to the 5. So these calculations are very, very hard. They involve hundreds of thousands of hours on high performance clusters. They're very complicated and they test our ability to do QFT calculations. And they are at 2 orders below the target for the next generation observatories. So I think it's fair to say that we're in the market for new tools that can simplify, especially this integration step. And this is exactly what we've tackled with this program here. And to be fair, this is not an apples to apples comparison. The calculation that we did today is simpler than the full two-body calculation. As I showed you, the calculation that we did today is a stepping stone towards the two-body calculation. Nevertheless, the fact that we were able to easily achieve such high accuracy, I believe, points to the fact that this is a viable path for the complete two-body problem. Okay. And with that, thank you for your attention.
So, thank you. Um, is there any question in the room that want to continue, that want to ask to our host? You can. I don't see.
I have one.
Okay, thanks, Kako.
Yeah. Hello again, Dimitrios. That was very, very interesting. Thanks for sharing.
Thank you.
So in your shell EFT framework, the loop integrals seem to not be as necessary, right? Like they are sort of already inside the exact black hole perturbation theory solutions, right? Or am I getting it wrong?
Yeah, exactly. Yes.
Okay. And is there like a deeper sense in which the like why the shell formulation makes the tidal response non-perturbatively like calculable without integration? Or yeah, that's the first question. Yes.
Um, well, by non, you mean the fact that we were able to obtain a formula, a non-perturbative formula, right?
Yes.
Why were we able to do this?
Yes.
So this, as far as I understand, as far as I know, this is okay. At least for this problem, the two-body problem, this is the first EFT truly in curved space. So it allows for this non-perturbative results. So if you start from flat space, you don't have access to these solutions. You know, you're building the metric perturbatively on top of the point particle. So there is no sense in which you have these solutions. But here, because we start from the curved space where, at least for certain pieces, we have all orders in the Kaplan expressions, you have a chance of getting it. And here we were able to get it. Does that answer?
Yeah. And do you anticipate that you can also do carrier black hole without integrating? Like, do you think it will be the same?
Yeah. Because these MST solutions, they exist also for care. So the most important ingredient is there. And yeah, in some sense now, what's missing is us figuring out, you know, how will the cell be rotating exactly, and that sort of thing. So it's nice because in some sense that's the fun question. The fun question is how do you write a nice model, a nice Lagrangian, and that sort of thing, rather than how do you do a very, very hard calculation. So yeah, so I believe it will be doable for care as well. Yeah.
Okay, that's very interesting. So maybe a second question very briefly. Maybe I got lost. Why do you need the word volume instead of, because your source is a word line?
So in the cell EFT, you replace the point particle with a cell. So instead of a word line, you have a word volume. So the
Oh,
source is not the point anymore. The source is really a cell, and that changes also the geometry. Instead of being sword-sealed all the way to the horizon, it's sword-sealed outside the cell, but inside it's flat space.
Ah, okay. Okay, perfect. Thank you.
Is anyone else with a question to our um to our presenter today? Let me see.
I think someone raised their hands. Ah, okay, no, they lowered their hands. Okay.
So I guess we don't have more questions. Well, thank you again for your presentation. It was very interesting for us, and I think we can give applause to the to our presenter to your presentation today. Thank you so much.
Thank you. Yeah, let me also say if you have questions over email, I'm very happy to discuss offline as well.
Thank
And
you.
thanks for having me.
Thank you.
Okay. Thanks so much, and I think we can finish the session. Thanks and goodbye.
Thank you. Bye.